Look at this dense wall of text. We've all done it, writing a mega prompt by mashing instructions, background context, examples, and the actual question together into one block, hoping the AI figures out which piece is which. When the structure is this flat, models often get confused. They might mistakenly follow a random sentence buried inside your source document, treat your data as a command, or hallucinate a format that doesn't actually exist. This is an information architecture problem. To fix these outputs, we have to look past the specific words and focus on the structural parsing happening under the hood. Major AI models process unstructured text in completely different ways. Currently, there are two distinct architectural approaches for setting boundaries: inline tagging and dual-channel separation. Reliable performance requires moving away from the one-size-fits-all prompt. You need to structure your text to match the native language of the specific parser you're using. For Claude, that native language is XML. Anthropic specifically trained their models to recognize structural boundaries using plain HTML-style tags. Wrapping specific elements in angle brackets translates a flat wall of text into discrete chunks. These tags can nest, wrapping a master documents tag around multiple files for perfect hierarchy. This provides four benefits: clarity, accuracy against adversarial inputs, instant flexibility, and easy code parsability. You can even apply this to complex reasoning by asking Claude to put its internal monologue inside thinking tags. Segregating the chain of thought from the final answer block allows your production code to cleanly extract the output while keeping the reasoning available for debugging. XML boundaries force strict structural discipline onto a flat text space, ensuring the model never confuses your context for an executable command. Google AI Studio and OpenAI use a different architectural logic. They abandon inline tags in favor of physical field separation. Boundaries are established by a dedicated channel called System Instructions. This persistent window defines the AI's persona and rules. Isolating mandatory constraints in this top window protects operational logic from being overwritten by raw data streaming into the user chat below. Unlike Claude, where you type the boundaries yourself, these boundaries are hard-coded directly into the user interface and the API structure. This dual-channel approach prevents prompt confusion by physically quarantining the model's instructions from the user's variables. To see the difference, let's build the same complex task across both architectures, summarizing a document using an expert persona and strict markdown rules. For Claude, we sequentially wrap the expert persona, examples, and source text inside distinct instruction, example, and document tags. In Gemini, we isolate that persona and rules within a top-level system window, routing the raw source document exclusively into the user window below. Both of these builds solve the mega prompt failure, but they use fundamentally different structural pipelines to reach exactly the same result. Mastering these divergent structural styles is the key to maintaining consistent task adherence across different models. At their core, large language models are sophisticated pattern matchers. Providing a cleaner, provider-specific structural input reduces noise, allowing the model to follow the intended pattern with much higher predictability. It is time to stop writing conversational prompts and start strictly engineering for the parser.